lecture. Yesterday we explained the basics of quantum mechanics from a quantum computing perspective. And today we're going to see how we actually build quantum circuits, what are quantum circuits, and then we're going to see how we can, let's say, query functions and things like that through quantum circuits. And then the first quantum, the early quantum, something like show separation between things you can do with quantum computers and classical computers, and this will be this will not only solidify our foundations of our understanding of quantum computation, but also prepare for tomorrow when we're going to talk about block encodings, which are a general way of let's say accessing information or matrices. Is that if we want to reach arbitrary states over here and arbitrary unitaries over here, we are doomed. So because there are just way too many parameters, right? It's going to have an exponential scaling. So we need to talk or reason about the unitaries or the operations and states we do expect to be able to reach in an efficient way, or like in a reasonable time. And those are specified by what we call polynomial-sized circuits or quantum circuits. Because again, if we just have n qubits and you want to do an arbitrary operation, then no way we're going to be able to do this. Okay, so let's again build intuition classically. So classically, a circuit is a sequence of elementary operations on bits. So, for instance, you can take you can implement some function g, which goes from n qubits to n bits to m bits, that only depends on a few bits. And these correspond to elementary gates on the device. So one example is just taking the naught of, let's say, bit 2. So if you're just given a bit string, let's say 0, 1, 1, and then it gets transformed into, we take the naught of the second bit, so it's like 0, 0, 1. And classical computers, they just work by having some sort of universal gate set, which in principle allows you to compute any function and then combining those. Okay, that's essentially how it works. Now, quantumly, what we'll have we'll have a tensor product of a unitary acting on a few qubits. For instance, we could have something like the unitary x tensor identity tensor n minus 1, where x is just this unitary. So, unitaries like this one can be specified efficiently, right? I mean, I just wrote it down and it didn't take me too long. And on top of that, you see that it only acts on qubit 1, right? It leaves all the other qubits alone. So the idea to build quantum circuits is to actually combine such simple unitaries that act locally, and then we expect that then on our device we have some sort of local interactions and so on, so that we can design such local operations and we can combine them together. And you know, in principle, if you only have one of these, then it's not too difficult to understand what's going on, right? But as you start combining them, don't forget that these are exponentially large matrices. So when you start combining them, you actually can model rather complicated objects, okay? So so how do we define then a quantum circuit in general? So first, so maybe definition. Given a subset A of the n qubits and unitary U acting on A qubits, we define U of A to be the unitary U acting okay. So in some sense we've ordered the qubits, okay, and then we put the unitary U acting on the qubits that are on A, and on the rest we don't do anything. Okay, so this is essentially this notation. And then what is then a quantum circuit? A quantum circuit is nothing but some ordered unitaries acting on a system. So given a set of unitaries G, and these are a subset of sorry, 2 to the k acting on k qubits, and a sequence of subsets A1, AM with AI of size k. We define the quantum circuit to be oh, I forgot the unitaries. Sequence subsets and unitaries U1 UM in G to be given by the unitary U acting on a M U. So what is then this quantum circuit? Well, first we specify what are sort of the operations we can perform, and we suppose that these operations are all defined on at most k qubits. So I tell you what I can do. Then later I tell you where you should do these operations. So these are these subsets. And as these elementary operations are on k qubits, they all have to have the size k, so that makes sense to apply them there. So essentially, this bit is telling you where you should act with the unitary, and this bit is telling you where what operation you should do. And this is the definition of a quantum circuit. So some remarks. So remarks. One, we usually take G to be finite. So there are many reasons why you would want G to be finite. Reason number one is that if you don't take G to be finite, this means you're assuming you're able to implement operations up to infinite precision, right? If you can implement some sort of continuous set of gates, and this is not reasonable, right? Doesn't matter what we're doing in life, we can only make things up to a finite precision. So this is not a reasonable assumption to say that you can do something like that. And reason number two for picking this set G to be finite is that it's actually super important later for error correction to assume that you can only do that you only do a finite number of operations. Otherwise, you cannot correct errors. But unfortunately, this is beyond our scope. But this should also sound a bit strange, right? Because, well, if I'm taking this set G to be finite, I actually want to approximate the unitary operators, right? And these are very much not finite. They are this continuous object, right? Or these states over here, right? They are also continuous objects. And if I only consider G to be finite, well, then clearly, if I can only do this many operations and so on, I will never be able to precisely capture all of the unitaries, right? Because again, I'm trying to approximate something which is uncountable by something that is very much finite. So there's some conflict there, but there is this fact. So there's this other fundamental fact, which is the Solovay-Kitaev theorem. And it says that if G generates the unitary group on k qubits, and G contains, or let's say is closed under inverses. Oh, where's the... here. G closed under inverses, then for any V element of U to K, there is a sequence, let's say U1, UL elements of G, such that the norm between is smaller than epsilon, and L equals at most log C epsilon minus 1 with some C that is between 2 and 3. Okay, so let's digest this fact in a second. So what does generate mean? So a subset of the unitary group generates it if I can, for any element of the unitary group, I can sort of get arbitrarily close to that guy by taking products like this one. So this is, if we want to approximate any operation on a quantum computer with these operations from G, then clearly we need to generate the whole group. So this is clearly a necessary condition. If the subset doesn't generate the whole thing, then we cannot, of course, expect to have this. And then we have this other assumption of being closed under inverses, which, well, you know, why not? So then it's saying, this theorem is saying, that in fact we can find an approximation that is not too long, right? So the number of these elementary operations I have to do scales polylogarithmically in the precision. Okay, so it tells us that as long as we can do these elementary operations well enough, then we can approximate whatever we want with an overhead that isn't too bad. Some further comments. First, in the recent years, there was some research trying to get rid of this assumption, and they were able to do it. Second, so in principle, this is no longer required, but the usual statement assumes this. Another thing is, well, what is this constant? What is the optimal constant over here? And the answer is, we don't know. So here's your first research question. You see that even some fundamental questions in quantum computing are still open. For instance, what is the optimal constant for the Solovay-Kitaev theorem? Okay, so questions on this? Mm-hmm. Yeah, I must. Yes. I probably, yeah, exactly. That's true. Indeed. But and I don't find this one very crazy. So it should be fine. Other questions? So just to mention, there are some standard gate sets. So usually, so I should also say that usually we only take k equals 2. So we only consider 2-qubit gates. And then you can take, just for you to have heard this, I won't explain exactly what they are, but the standard choice is to pick G to be Clifford plus T. So these gates, so the Cliffords, they are so they are generated by the following unitary matrices. There is what we call the C0, which is a 2-qubit gate. So this is the C0. Oh, why did I write it like this? C0 is this. You have the Hadamard, which is we're gonna see a lot of the Hadamard today. Oh, I screwed. No. So this is the Hadamard and S. So 1 EI pi over 2. So you look at, so you take, these are you take the group generated by these guys. These are the Cliffords. So these are the generators of the Clifford. And then the T-gate is just EI pi over 4. So it turns out that if you can do the group generated by these and this one, then you can approximate anything. And this is what most people try to do. But there are other universal gate sets that are popular. Okay. So before we continue, I'd just like to quickly explain to you circuit diagrams, because whenever we're working with circuits, I mean, this is like a formal definition, but this is not how you would represent circuits in papers or when reasoning about them. And the way we do it is usually through circuit diagrams. So they are represented like this. So first, you specify the input state. And in this case, we're just taking the input state to be 0, n. That is, we have n qubits, and on each qubit, the initial state is 0. And then you have wires coming out of these qubits. And these wires can then take as input, can be the input to other gates. So for instance, here we could do some unitary U1. Here we'll do a unitary UN, which we specify. Then after this, we can do, for instance, a 1-qubit gate, which would be like this. Or let's say the S, and here we could do the X, and here we could do, I don't know, another H, and then continue. So these things here are then unitaries. So essentially, if we go back to this notation over here, like I'm saying that I'm applying a certain unitary, and the wires are indicating which are the qubits, right? And then we can combine these operations, a bunch of them, and at the end, we usually draw something like this, which indicates measurement in the computational basis. So essentially, in these diagrams, instead of telling you like defining a quantum circuit that way, I just essentially draw which unitaries are acting on which qubit, and at the end I'm telling you I'm measuring all of them. Okay. Questions regarding this? Nope. Then let us now work with what are called quantum queries let me change the order a bit, and let's first do something which maybe not might be a bit boring at first, but I promise to you it's important, which is how to do classical computation with quantum circuits. So So I told you that in principle, if I can, so this theorem sort of tells me that if I can do these elementary operations, I can combine them in clever ways, and I can decompose any unitary on k qubits as a sequence of those operations. And there is something else that is quite important, which is that then I can decompose any unitary I want into unitaries only acting on k qubits. So in principle, I can, using these elementary operations, approximate any unitary I want. So these are the things we can do. But then one question you can ask is, what can I do in this computational model, and can I actually compute things that I can compute efficiently classically? And the reason why this is not obvious, like can I do whatever I do with classical computers in this model, is the following. So if you open a textbook, what are usually the some of the standard gates people use for classical computation? They use, for instance, gates like the logical AND, or, right? And what is the problem with these gates? So like standard classical gates. So let's take, for instance, the OR gate, right? So what is the truth table for the OR gate? So if the two first inputs are, so like input 1, input 2, output, right? If it's 0, 0, it's going to be 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. So this is the truth table. Now, why is it not so classically you need functions like these ones in principle. These are like the standard building blocks of classical circuits. And why is it in principle not obvious that we can reproduce things like that on a quantum computer? What are some immediate problems we recognize? So note that if I have a quantum circuit, it's always specified by a sequence of operators, of unitaries, right? So in principle, if I implement a quantum circuit, or I tell you what a quantum circuit is, so if I tell you a quantum circuit U1, U2, Um, then I can also tell you how to revert that quantum circuit, right? I can define U dagger, which is just, I'll just have to revert the other of operations. So if I start at a certain state 0, then I can apply all these operations. then I can apply U dagger, and I get back to exactly where I started from. Now, in this case over here, this is impossible, right? Because this gate here only has two inputs and only has one output. So I cannot reverse the computation once I performed an OR gate, right? Because, for instance, all of these inputs over here are indistinguishable after I put an OR. They will always give me a 1. So I cannot go back when I use gates like OR in a classical circuit. They are not reversible. So like standard classical gates are not reversible. Unitary circuits are reversible. And this is a conflict, right? Because of this property, you might say, well, then maybe using these unitaries, I cannot even do something like a stupid OR gate on two bits. Because it's not reversible, I cannot represent it with a unitary, right? However, there's a way out of it, and this is a standard thing in quantum computing, which we're going to see tomorrow as well, which is when you face these problems that, in principle, all you can do is unitary on a quantum device. The reason to get away with it is to introduce auxiliary systems. So we're just enlarge the space, and then usually we can get away with unitaries. Okay, and let me explain to you what is a standard way of doing this, which is through the Toffoli gate. So a Toffoli gate so this is a gate on 3 qubits, and it is known also as acts as a control not. Okay, so I'll just essentially what it does is it only flips. So you have 2 bits. So you have input 1, input 2, and input 3. And if input 1 or input 2 not 1, it does nothing. And if input 1 equals input 2 equals 1, what it does is it flips bit I3. So that's essentially what it does. And what you can see is that it's actually a permutation. It just permutes and as it's a permutation on 3 bits, it can actually be implemented as a unitary on 3 qubits. So because it's just a permutation and we can have it as a unitary, in principle we can also implement the Toffoli on a quantum computer. And why do we like the Toffoli gate? So here's a fact. We can represent and, or, and fan out gates with Toffoli plus auxiliary qubits. So what do I mean? Let's give an example. Let's say we wanted to do the AND gate. So you can see that if we do the following thing, we do A, B. These are our two input things, and we want to compute the AND of these two. I claim that this, if we put the Toffoli, which we represent like this, then this output will be AND A and B. Why is this the case? Well, we only want this thing here to be 1 if we have 1 here and 1 over here, right? Because this is the only instance when AND should be non-zero. Well, indeed, if both of these are 1, then the Toffoli flips the third one. And we see that indeed we'll have a 1 over here in this case. And if one of these is not 1, then this gate will not do anything. So if our input was 0, we're going to get 0 over here as well. So we see that with the Toffoli, we get A plus B. So we keep our input A, we keep our input B, and in the third register, we have the result of the AND gate. So in this way, we made applying an AND gate a reversible operation. We can go back from here to here. We didn't lose any information. And all we needed to do was to add one auxiliary system over here. Okay? So the fact number 2 is that AND, NOT, and fan out are universal for classical computation. So what this implies in particular, what is a nice corollary of this observation, so what is an important corollary? Given a classical circuit with M gates, we can transform it into a unitary circuit with M Toffoli gates and O of M auxiliary qubits. So this is actually super important. The first reason why this is important is because, well, it tells us that if we have if we can do Toffoli and we can do additional qubits, then we can actually use unitaries or reversible circuits to compute whatever we want. But the second reason this is super important is that it gives us a recipe to, let's say, if we have a circuit that computes a classical Boolean function or whatever, then we can efficiently convert it into a unitary circuit that in principle will compute the same function, but now this is given in quantum form. And as we'll see in the second, after the break, the fact that we can also efficiently obtain such unitaries from classical circuits will allow us to do much more powerful things with these functions and even sometimes get exponential speedups. But that's for the second half. So just before we go for the break, what did we see now? We defined quantum circuits. We observed that they are reversible, which at first is maybe at odds with standard ways of looking at classical computation because it's usually not reversible. But with the help of the Toffoli gate, it is actually possible to just pick any circuit defined in terms of AND, NOT, and fan out, add a few extra systems, and you're good to go. You can actually get a quantum circuit that does the same thing. All right, questions before we go for the break? So before we move on to the next bit, I would just like to write this bit out as a circuit diagram. So what this means is that if you're given some function f that takes as input, let's say n qubits and spits out, sorry, n bits and spits out m bits as a classical circuit or as an efficient classical circuit, that is the number of gates is polynomial in n, then there exists efficient quantum circuit, that is we only require that only has poly n gates plus poly n qubits, such that, so we can have the n bits as input, and then we require some auxiliary bits. They are all set to 0. Then we do this big circuit R, but as I said, it's efficient. Okay, so and then here on the first m wires we have f of x, and here we have 0, 0, 0. Okay, so if we are given some sort of efficient description of a circuit that computes a function, then we can also build a unitary like this. Okay, now that we've established this, let's talk about queries through a function. Okay, so let's say quantum queries. As usual, we don't really want to get some intuition. It's good to start with classical queries. So, given some Boolean function on n bits, we have a black box that implements f, and we want to determine if f has some property for instance, for all x, f of x equals 0 with a minimal number of uses or queries to the black box. And what is a query? You give as an input a bit string, and you get as an output f of x. Okay, so just an and then in query complexity, you ask the question of how many times or how many questions do I have to ask before I can determine whether a function has a certain property or not. Okay, so let's take, for instance, the case of determining this property, that for all f, for all x, f of x equals 0. What is the worst case query complexity of this problem? Any ideas? So let's say you ask it for the all 0 string and you get 0. You get it to the, you ask the for 0, 0, 0, 0, 1, you get 0, and so on. How many times do you have to ask in the worst case before you can be sure that for all x, f of x equals 0? Not just the number of bits already. Like, it's the query complexity is 2 to the n, right? Because you have to ask all bits. So why do we like query complexity? Well, because usually getting lower bounds on how long it takes to solve a problem is essentially impossible. Nobody knows how to do it. It's a mess. But this is a setting where it is actually possible to sort of easily get lower bounds on how difficult it is to solve a problem. For instance, this property over here, it didn't take us a significant amount of effort to establish that in what was the query complexity for this problem. So I'm not saying that query complexity is trivial, but it's this sort of setting where you're given black box access to a function and you want to know how many points you need to evaluate before you can determine a certain property is one where it's actually possible to prove things. So that's why we like it. And so this is what a classical query is. And now I have to tell you what a quantum query is. And this will be, so the reason we're doing this is twofold. First, it will be a setup where it's sort of easy to prove quantum speedups. So I think it's nice to see a quantum speedup proven and so on, but it will also familiarize you with notions of like quantum oracles, which will be important tomorrow when we start doing quantum signal processing. So, and this is like a simpler form of a quantum oracle, okay? So our next goal is to try to model how one would sort of do this this thing, like a quantum query, in a quantum setting. And over here, I sort of already explained or already give you a hint of how we would do this, right? So whereas here we assume we have a black box such that we can put an input and it computes the function, what we'll do quantumly is we're going to assume we have a black box, a unitary operator, that given the inputs of this function, will in one of the outputs put the value of the function, right? This is how we're going to do things. So so we are given quantum oracle access to a function f in the form of a unitary operator O of f. It's gonna take as input n qubits plus 1, okay, and it's gonna output n qubits plus 1. It's unitary, has to be the same, right? And how does it work? Well, O of f on x b. So just to be clear, this is a n bit string, and this is just 1 bit. And when we do, so when we input something with x and a b, what do we get? Well, we get x and f of x plus b. Okay, so recall that f was either 0 or 1. So our output will also be either 0 or 1, so it can fit in here. But we have to make things reversible, so that's why there's this plus b. So in essence, what it does is it keeps your input, and on the second register, if b is equal to 0, it will tell you what the value of the function was. And vectors of this form, they form a basis for this space. So if I specify it on the whole basis, I get a unitary operator. I completely define the linear operator. And it maybe doesn't take you too much time to convince yourself that if you do it this way, it's actually unitary. Okay, it's not too difficult to revert the thing. You only have to add f of x again. Okay, so this is indeed an interesting thing and or object, because in principle now we can use this oracle on arbitrary quantum states. Okay, and why isn't it not crazy to assume we have a thing like that? Well, because of that construction over there. So if over here this black box is actually some some polynomial size circuit that computes this function f, then I know that if I'm given that circuit, I can also build this quantum black box in an efficient way. Okay, so we're not cheating in an insane way when we're assuming we have this quantum black box. I know how to build it if you tell me what is in the classical black box. Okay, any questions? Yeah. So essentially, for if you tell me, like, if you decompose this black box in terms of AND, OR, and fan out, I can then convert it into like a bunch of Toffoli gates and extra qubits. Yeah. All right. So, and then now that I defined this oracle, what is a query? To O of f, I can use of the unitary. So every time I use the unitary, I count one query. And then it's not difficult to convert, for instance, quantum queries into classical queries. Okay, because how do I do this? Well, if I wanted to ask this question for a given x, all I need to do, so like from quantum to classical, how do you do it? Well, if you wanted to ask what f of x was, you just do x 0. You feed this to O of f. What you're going to observe is f of, what you're going to get is x, f of x. So if you just measure this thing, it's going to be either 0 or 1. So you're going to observe the value of f of x. Okay? So going from quantum to classical is easy. So in particular, it follows that the quantum query complexity is at most the classical. Can it be much lower? Of course, the answer is yes. Otherwise, I wouldn't be doing this. And let's see what are some interesting tricks we can do with this object. Okay, and the first thing is to look at the following circuit. So 0, 0, 0. And this 0 here will be the auxiliary qubit of the quantum oracle. And then I'm gonna apply a bunch of Hadamard gates. I'm gonna recall you what these are in a second first. And then I apply the oracle. And then let's see what we get out. Okay. So okay, so let's first recall what the Hadamard gate was. So Hadamard is 1 over square root of 2, 1, 1, 1, minus 1. So if we look at Hadamard of 0, it's just gonna be what we call the plus state, which is 1 over square root of 2, 0 plus 1. Okay. But now we are doing n of these in parallel. So the state, so let's call this here step 1. So the state over here will be Hadamard on 0 tensor n. So this will be 1 over square root of 2, 0 plus 1 tensor n. And what is this thing? What do we get here? Well, when I expand it, I get all possible combinations of zeros and ones, right? Because this is like taking a product. So every time here I get 0 and 1, and I can combine them in arbitrary ways. And here I have this prefactor in front of it. So this state is actually 1 over 2 to the n half, because I'm going to have this square root of 2 n times. And then a sum over all possible x's. So this is called a uniform superposition. Okay, so now what is the input state here at step 1? Well, it's gonna be, so at step 1, it's gonna be 1 over 2 to the n half sum x. X and x are all possible bit strings. And on the auxiliary qubit, it's gonna be 0. What happens if we now query f, sorry. Well, it's a unitary operator, so it's linear. So we know what happens when we apply x, when the input is x and 0. The output is going to be x and f of x. But now we have a linear combination. So to get the output, so if we apply O of f to, let's call this state psi 1. So if we apply O of f to psi 1, what we get is 1 over 2 to the n half x okay. So this is our output. Now, why is this interesting? This is interesting because now, in principle, we asked questions in superposition and got the answers in superposition as well. So we have this superposition of x and the value of f of x. And this is not something you can do classically. Okay, this is strange. So sometimes you read people saying like, oh, like quantum computers solve problems by testing all answers in parallel, which is not true. But one reason people have this misconception is because we have the power of doing things like this. We're like querying the function at all values in parallel in some sense, right? But now we actually have to do something with this, because if we were to measure this, what would the outcome be? Like having the power to do this on its own is not particularly useful, right? So what happens if we measure in the computational basis? Does anyone know? Well, what happens is that we get uniformly random pair x f of x. So we're going to observe some x uniformly at random and the corresponding value. This isn't particularly powerful, right? I don't need a quantum computer to ask random questions. So we need more. We need to do more if we actually want to use the power to prepare this state in a more constructive way. And we're going to see in a second in the toy problem how we can actually do this. But before we do that, I would also like to comment on what is called the phase oracle, because here we always set this other input state here to be 0, but in principle we also have some freedom here. We could choose a different input state, and maybe this is also helpful, and it turns out to be the case. So before we talk about Deutsch JOSA, we'll just define the phase query. So right, so given f, again a Boolean function, we define OF plus minus, just to say that this is a phase oracle, to be acting as follows. So okay, so before, did I just erase the definition of the I think I did. Sorry. So, okay, what was the usual oracle? You had OF x0, and you got x f of x plus, it was b, sorry. You got this as an output, right? So somehow the information about the value of f of x was in the second register. Here now we're going to instead assume that the information about the value of f of x will be put in this phase over here. So that's why it's called a phase oracle. And it turns out that if you just do, if I give you this thing, it is indeed true. Oh, sorry. I actually wanted this. It is indeed true that if you just put the second system to the minus state, you get the phase oracle. So if you're interested in having the information about f to be in the phase instead of the second register, all you need to do is to, instead of feeding the first state to be 0, you just put it at minus. So again, why am I telling you this? I'm telling you this because this shows that assuming I have access to a phase oracle isn't crazy. If you give me the circuit that implements this function f, classical circuit, I can write down a phase oracle for the same function. Okay, so I'm not cheating. Okay. All right. I think. Yeah, I don't know. I mean, now would be a good time for a break, but we only did like 30 minutes. Now let's do Dodge Josa. I think we can do Dodge Josa in 15 minutes. Okay, so now we're gonna discuss our first quantum speedup, and it's gonna be in this query complexity setting, and it's a very artificial problem, but it's easy to state, it's easy to prove, so that's why we do it, and also for historical reasons. So I think it nicely illustrates what the sort of tricks you can do with quantum computers. Okay, so Deutsch JOSA. So this is from 98. And what is the problem setting? We are given some f, 0, 1, n, to 0, 1, with the promise that f is either balanced. I'll explain what this means in a second. That is, for half of the inputs, or constant. Our task: determine which is the case. So maybe before we go to the break, we solve the classical query complexity. So how many queries do I need to the function f to decide if it's balanced or constant in the worst case? Any ideas? So yeah, exactly. So it's 2 to the n half plus 1. Why is this the case? Well, you know, how is an algorithm to solve this problem specified? Well, it's specified by you give me a list of the points where you like to know the value of the constant, and some devil could be adversarially picking the function f, such that you know, for precisely those values, the function is always 0, and only after you've asked this many questions, you're going to see a point where the function is actually 1, and then you see it's actually balanced and not constant, right? So this is why this is the query complexity, because it doesn't matter which instructions or which questions you ask, you always need this many before you can be sure, right? So this is why this is the classical query complexity. But what is important to say is that this is deterministic. Because if you, Ruben, you have a question? Huh? Due to the sorry. Yeah, sorry. Yeah. Sorry. Yeah, exactly. Um, Indeed. Sorry. Uh, right, because half of you need to look at half of the inputs plus one to be sure. Um, but this is only for deterministic strategies, right? If you allow for a small error, like or small probability of failure, then the query complexity is very low, right? It's essentially constant, because if you're allowed to pick your questions at random, right, then you at every step, if the function is balanced, you have a 50-50 probability of getting either 0 or 1, right? So if the function is indeed balanced, and you ask, let's say, m questions, the probability of you only hitting the same thing always decays exponentially with the number of questions you've asked. So if you're asked to ask questions, if you're allowed to ask questions at random, then the number of queries you need to reach, like say, a constant confidence is constant. So so if we allowed for probabilistic, it's actually constant. So this is one reason why you might say, well, I don't like Deutsch-Jose. And another one is because, of course, this problem is a bit artificial. But before the break, after the break, we're going to show that with quantum queries, you can solve it with you can solve it with one query. Which already shows you a huge speed up. So yeah, but let's leave that for after the break. Okay, so let's do 5 minutes. All right. Let's do now Deutsch-Jose. So, okay, the circuit is actually very simple. The way we solve Deutsch-Jose. So here is the circuit. We start with n zeros and a minus, so we're doing a phase oracle. Then, as before, like when you start studying these quantum algorithms for these query complexity problems, the first step is always to apply a bunch of Hadamard's, so that we do these queries in uniform superposition. And then use our oracle F. After that, we again apply a bunch of Hadamard's. And this qubit we don't care about anymore. And here we just measure them. Okay, so let's call this psi1. Let's see the state here as psi2. the state over here, psi free, and then we measure. So what is psi 1? This is something we already discussed before. When we apply a Hadamard to each one of the qubits, what we get is a uniform superposition, and this guy we leave untouched, so it stays the same. So psi 1 is 1 over 2 to the n half sum x in 0, 1, n x minus, right? So as I mentioned to you before, if this initial state here is in the minus, this acts as a phase oracle. So, which means that once it goes through this oracle, the value of the function will be imprinted in the phase in front. So this will be 1 over 2 to the n half sum x 0, 1, n, and then minus 1 f of x, x minus. Okay, now we need to apply the Hadamard gate on each one of these qubits, okay? But before we do that, let me tell you a fact. If you have age of n, like n Hadamard gates, acting on a bit string x, what you get out is the following thing. So sum of j minus 1 x times j over 2 to the n half times j. So, and this, I mean the product as bit strings. So, you know, what you do is you take each entry of the bit string x and multiply it with each entry of the bit string j. Let me be a bit more explicit that this thing is a bit string, and you just add them up. And if this is even, you get a 1, and if it's odd, you get a minus 1. So this is how the Hadamard acts. Okay, so by linearity, we know how the H tensor n will also act on psi 2, right? So H tensor n on psi 2 is then equal. We'll expand the sum now also in terms of j, okay, so that we can see what's going on. It's going to be 1 over 2 to the n. Then we have first the sum over x of minus 1 f of x, and then we have the sum over j minus 1 x times j, and then here we have j and minus. Okay, now let's look at what happens. Like, what is the probability of measuring j equals 0? So here's where the magic happens. So if j is equal to 0, this thing here will always be 0. So we see that the total phase in front will be given by f of x. There are no like sign cancellations going on and so on. So as minus 1 x times j equals 1, the probability is just sum x minus 1 f to the x 1 over 2n and this thing squared. Now, why did the magic happen right now? We know that this function is balanced, right? So, sorry, it's either balanced or constant. If the function is constant, what will be this thing? I mean, this f of x will always be either 0 or 1. So this thing, so if f is constant, it follows that the probability is 1. So, and what if f is balanced? Well, in this case, for half of the inputs, f of x will be 0. For the other half, f of x will be 1. So we'll get like this sum will be 2 to the n minus 1 minus 2 to the n minus 1. So it will be 0. So the probability is 0. And so what is the algorithm that has quantum query complexity 1 to solve this problem? Well, you implement the circuit and you measure these bit strings. If you observe the outcome 0, you declare that the function is constant. If you observe any other outcome, you declare that the function is balanced. And we just showed that this works with probability, with success probability 1. So there's not even like a small probability of you making a mistake. You'll always get the right answer if you do this with only one query to the oracle. Okay, and 1 is usually much smaller than this. So this gives a huge advantage, right? But again, this is a rather artificial problem, but it shows us how having access to quantum queries can be very, very, very powerful. And what were sort of what was the main trick over here for this Deutsch-Joseph thing is that let's say when we look at how the phases behave for f of x, then we have this very nice regular behavior, and this is something where that is usually the case for these quantum speedups in terms of query complexity. The reason why they work is because you usually assume that f has some form of symmetry, like here, like there's a lot of structure for f, and these sorts of circuits can exploit this structure. So before I continue with these comments, any questions on why this works, or was it clear? Okay, so maybe one question, a few comments more. If you dislike the fact that quantum loses against, or not loses, sorry, if you allow for a constant probability of failure and random questions, then you can also do this classically, right? But if you don't like this aspect, then there's a variation of this problem, which is called Simon's problem, where the whole structure is simple, but then you can also show a huge separation between quantum and probabilistic. Okay, so you could argue that even against probabilistic, it's a bit different, right? Because here we know with probability of success like 100% what is the case. There we cannot be like 100% certain, so it's still a separation, but not a separation in practice if you allow for small errors. But with this Simon's problem, you can actually even get a separation with respect to probabilistic algorithms. And these sorts of constructions were what inspired Shor. So these were like the early algorithms that led up to Shor. Okay. Questions before we move on? Nope. Okay. So in some sense, I showed you how we can play with classical Boolean functions with a quantum device. So we can make these queries to the function f, and potentially determine whether it has a property or not in a faster way. Yesterday I mentioned Grover's algorithm, and Grover's algorithm is also just a very smart way of using queries like this one. So if you want to read up on Grover's algorithm, you now have the required knowledge. But we are getting ready for the more let's say substantial part of the course, which is going to be about quantum signal processing, which is going to be about not processing Boolean functions on quantum computers, but matrices. Okay, which requires a more complicated access model. And before that, one last piece of fundamentals we are missing are so-called controlled operations. Maybe I can erase this. Okay, so given a unitary U on n qubits, we define the controlled U on n plus 1 qubits as the following unitary. So if you apply controlled U to 0 psi, it will give you 0 psi. And if you apply controlled U to 1 psi, it's gonna give you whatever happens when you apply U to psi. So essentially what this controlled unitary is doing is you add one more qubit, which is what we call the control qubit, and so this is the control, and this thing over here is the target. Okay, and what is the idea? This qubit over here is telling you whether you should apply the unitary or not. And I already mentioned one control unitary in the course, which was the C naught. So how is it defined? I wrote down the matrix and I said it's like this. How does it work? Well, if you expand it, it actually works like this. So it's of course control and then not. So it acts if the first qubit is 0 and the second qubit is x, then C naught of this will not do anything. This is this block of the matrix, and C naught of 1x will just be 1 naught of x. So, you know, if this was 0, it will be 1, 1, 0. So this is a classical example. But the nice thing is that we can apply this in superposition, and then things become more interesting. Okay, because these controlled gates are one way of creating correlations on a between qubits. So, for instance, and on a circuit, if we do the following thing. Oh, sorry, that should be C, it should be U. So this thing over here is the control, and this here is the unitary. So unitary / target. So whenever we draw something like this with like this little dot over here and here the unitary, this means that this is the control qubit and this is the target qubit. And just one simple example of a circuit that will illustrate how these controlled operations can be pretty powerful. Is this very standard circuit. So we start with 0. We do a Hadamard on the first one, do nothing, and then we do a C naught on them. So let's see what happens. So this is, oh no, this is psi 1, and this is psi 2. So what is going to be psi 1? I mean, we start with 0, 0, right? And then we apply a Hadamard on the first one. So psi 1 is going to be plus 0, which is 1 over square root of 2, 0 plus 1, 0. And we can further expand this as 1 over square root of 2, 0, 0, plus 1, 0. So now let's do the controlled knot. The first qubit is the control one, and the second is the target. So what do we get here at psi 2? Well, for this one, the control qubit is 0, so nothing happens. So we get 0, 0. For this one, the control qubit is 1, so we have to apply a NOT gate. So we get a 1, 1. And this is what we discussed yesterday. This is the maximally entangled state. Now, why do we find this why is this interesting? Because it shows that, for instance, these control or 2-qubit gates can actually, as we argued yesterday, create states that have interesting correlations between the qubits. But for the second part of the lecture series, what will be important is to note the effect we had in sort of letting the control qubit be in superposition. Because this way, we were able to apply or not apply the unitary with different weights, right? So more generally, so more generally, um, we have that if we apply C naught to alpha 0 plus beta 1 0, we get alpha 0 0 plus beta 1 1. So by picking these different weights over here for the control system, we can also apply the unitary with different weights, right? So in some sense, we can do like linear combinations of the identity operator and the not operator in this way. Okay. All right. So any questions about controlled operations? One last remark is that we can also consider multi-qubit controlled operations, and these are then ones where instead of just having one qubit over here, we have many, and all of them have to be one for something to happen. So it's like a natural extension of what we did. Okay, so in principle, this was what I today we're going a bit faster than yesterday, and we can actually already start with the last bit of the lecture, which should be a bit more exciting, which corresponds to block encodings. So now that we know controlled operations, we can start playing with block encodings. Okay, so block encodings. So as I mentioned, I told you how to play with functions f from 0, 1, n to 0, 1. But now, let's say unitaries are matrices, right? They're big matrices, and therefore it should come maybe as no surprise that people think that quantum computers should be also great to manipulate big matrices, right? And I explained to you what is the sort of input model. So what was the input model for this function f we had before? Well, or let's say access model would be a bit better actually. It was this O of f object, right? But now, how do we access matrices? On a quantum computer. And the answer to that are block encodings. So, well, what the name already, so let's say we are given a let's say 2m by 2m matrix. Okay, then we can implement unitaries on a quantum computer. Okay, so if we're just given a matrix A, in some way we have to massage it into a unitary operator. Okay, and block encodings are one way of doing this. So the first thing we can observe is that um, I can find a 2 to the 2m by 2 to the 2m unitary u such that u equals here I put a over the norm of a, and here I don't really care about what's going on. Okay, tomorrow I'm gonna give you some explicit constructions of a uniform of a unitary of this form. But what is the general idea here? I mean, this is sort of a necessary condition that I normalize A by the operator norm of A, because you know, like the rows and columns of a unitary matrix always have to be 1. So if I have rows or columns that have norm larger than 1, then of course I cannot put this inside a unitary operator. So like the sort of normalization with the operator norm is always necessary. And but the idea here is sort of similar to what we were doing when we were looking at reversible circuits. So I know I cannot, I mean, quantum computers can only do unitaries. So what am I, but I want to play with an arbitrary matrix. What do I do? Well, if we forget about this normalization, what we are actually doing is we are adding some extra garbage we don't really care about, and putting the unitary this matrix we care about in a particular corner of the space. So we add some auxiliary systems to be allowed to look at this unitary A on in a corner. Okay, so generally speaking, so given a matrix A and a unitary U, we say that U is a block encoding of A, if we have that identity let's do equal here. We will generalize this definition a bit later, but what is then the idea? We look, I mean, this function, this part over here is telling me that if I project down into a corner of the matrix U, and I know which corner, okay, then this unitary is gonna act like my matrix A. And this is somehow what a block encoding is, and the name should hopefully be intuitively clear, right? Because we are encoding this matrix A into a block of a unitary. And what is then the goal of quantum signal processing? The goal of quantum signal processing is, given a block encoding of A, obtain of A and some, I will be a bit vague now, but we'll be more precise tomorrow. And nice function f, let's say from -1 to 1 to -1 to 1, implement a block encoding of f of A. Okay, and maybe just one comment. So just one remark. For for A Hermitian matrix, we define f of A through spectral calculus. That is, so if A has a spectral decomposition A lambda I, or VI say, then f of A is defined as some I f. So we just apply the function to the spectrum of A and keep the same eigenvectors. Okay. So this is the goal of quantum signal processing in a nutshell. We are given, let's say, some very smooth function or some polynomial or like trigonometric polynomial and a block encoding of A. And our goal will be to be able to apply this to the matrix A. Okay, this is roughly what we want to do. So there are a couple of questions you should be asking yourself now. Question number one is, where is this coming from? Like, why am I assuming that I have this? Like, how do I get this? Does it appear out of a miracle or whatever? Because remember that when we started when we were talking about Boolean functions, then this oracle, I hope that I convinced you today that this isn't a crazy object. If I have a circuit that computes this, I can get this. But like, if I'm given a matrix A, like, how do I get this? Okay. So this is something we'll discuss tomorrow, and we'll discuss it in two cases that are super important. So namely, okay, let me make me a list. So what is on the to-do list for tomorrow? So for tomorrow, how to construct block encoding, and we're going to do it for two very important cases. The first one is when A is a sparse matrix. Okay, so we're going to assume that A only has a certain number of non-zero entries per column, right? And another case that is important for physics, when A is sum of Pauli's. I think I didn't introduce Pauli's, right? Okay, I'll introduce Pauli's tomorrow as well. Sorry. And maybe an even more important question is, why do I want a block encoding of f of a? Like, who cares? I mean, why am I going through this trouble? Okay, and as I said, sort of the thing we are aiming for really is to solve linear systems of equations with quantum computers. And for that, let's, in the last few minutes, explain why, for instance, that problem can be solved using this sort of framework. So let's do an example. Okay, so we're going to assume that the spectrum of A is going to be contained between -1 and kappa. Oh, minus kappa, sorry. And kappa and 1. So what is this assumption about? This assumption is essentially telling us, oh, I should put this. So this assumption is essentially saying that the condition number of A is at most kappa. So let's say you want to solve a linear system of equations specified by A. How difficult will it be? We know that systems of equations, they don't admit a solution once once we have zero eigenvalues, right? So in some sense, what I'm saying is I'm given some promise that I won't be too close to zero. That no matter what I'm doing, like this matrix A will have eigenvalues that are well behaved, and this parameter here is telling me how well behaved they are. Now I can define the function f of x to be what? To be kappa times x minus 1. And what is the or no, sorry, kappa minus 1. What is the nice thing about this function? Well, if I apply f of a to this function, it will be kappa minus 1 times a minus 1. And because of this assumption, we have that the spectrum of A is contained in minus 1. Sorry, spectrum f of A is contained here. So if I apply this function f to the matrix A, I'll get something that has spectrum between minus 1 and 1. So it fulfills the conditions of this quantum signal processing thing. And, well, why would it be super nice to have something like this? If we did this, then we would have a unitary V that looks like what? Well, on the upper corner, upper left corner, we would have A minus 1 times kappa. I would be able to tell you how to construct such a unitary. And over here, I'm hiding the matrix that solves the linear system of equations that is specified by A. Okay, so if we can do, for instance, functions like the inverse function and then get block encodings, we'll be able to solve linear systems of equations. Okay, so this is, for instance, one motivation why you would might want to like be able to do these things. But let's say you're a physicist and you actually care about simulating time dynamics, right? So what should I erase? Maybe that bit. Suppose now take f of x to be e to the I tx, right? If we could do block encodings for this thing, then what you would get is that in an upper corner of the matrix, you have e to the iat. So for the physicists in the audience, if A is like a Hamiltonian of a system you care about, this bit of the unitary will then correspond to the time evolution defined by the Hamiltonian A, right? And then, so in principle, if you have a block encoding of your Hamiltonian, and you can do quantum signal processing for this function over here, then, well, you could also simulate time dynamics. So we see that this sort of framework allows you to do a bunch of things you'd like to do in physics or in solving linear system of equations. And the reason why we like this quantum signal processing framework is precisely that, because it gives you one sort of toolbox to do things like simulate quantum dynamics and at the same time simulate linear systems of equations. But the only things we now need to specify are how do we get these block encodings, and given a function f, how do I use the block encoding for A to get a block encoding of a function I care about? Like, what are the properties of f that determine how difficult it is to transform this, let's say, into that? And this is what quantum signal processing is all about. And maybe one last comment before we finish today. Another thing you should always be careful about is this output form, right? Because I'm only telling you that we will be able to implement a unitary such that with this right corner it will look like what we want. Okay, but this is a very different output form than what we have in, let's say, when we usually multiply matrices. Because I'm only telling you that I can implement this unitary on a quantum computer, and for instance, I cannot write down all the entries of this on a piece of paper. And typically this will be an exponentially large object. So another thing we'll have to be very careful about tomorrow and the day after that is on what this output form actually is. Because it's just like one corner of the unitary, and then we can apply it to other quantum states and so on. But this is very different from what we usually have when we're working, let's say, with classical devices, where we usually have some sort of list of all the entries and so on. Here it's just like some unitary we can work with, and then we need to prepare quantum states and so on to play with it. All right, so this was like the brief overview of block encodings and quantum signal processing and why we care, and hopefully this will set the agenda for the other 2 days. Like our goal will be to again see how to implement the different functions and how to get these things, and then finally, once we understand that, we can, for instance, analyze a function like this one or that one to get a bunch of applications for free. Okay, questions? Nope. Okay, then let me repeat what I did yesterday. Any feedback or comments for tomorrow? Any wishes? Too fast, too slow? All good? Well, perfect then. Okay, then see you tomorrow.